Hello and welcome to another electricity and magnetism extra practice video. Today we'll be discussing electric field mapping. As always, all information and questions are used from the Essential Calculus-Based Physics Study Guide Workbook Volume 2 by Chris McMullen. An electric field map shows the electric field lines or lines of force and the equipotential surfaces of charged objects. A line of force is the direction a positive test charge is pushed at any point in the diagram, and an equipotential surface are just surfaces or wavefronts where the electric potential is constant. An example of a field map would be this. Say we have a positive point charge here. If you have a positive test charge, the field lines would be out, away from this positive test charge, positive point charge. And as the arrows extend into infinity, there are points around the where the volt or the electric potential is constant. For example, this could be 5 volts. Farther out could be 4 volts. You will notice that as you get closer and closer to the center, that the equipotential surfaces will get closer and closer together. There are some rules for electric field maps. The first rule: force lines travel from positive charges to negative charges, or by decreasing electric potential. Therefore, positive test charges will essentially be an origin point for the field lines, while negative point charges will be an endpoint, having resulting in field lines around these charges to be reflective of something like this, where the field lines are being emitted from the positive point charge and the field lines are converging towards the negative point charge. Second, force lines are perpendicular to equipotential surfaces. It can be seen as that if you were to take a positive test charge and keep going until the points where the field lines are appear to be parallel, that the surfaces will be perpendicular. 3. Force lines cannot intersect. If you were to have two positive point charges, 4 equipotential surfaces cannot intersect. And finally, force lines are perpendicular to the charge conductors. Here are some of the equations that you need to know regarding the electric force. You have your electric field is equal to length of constant times the absolute value of the charge divided by the distance from the charge squared. And then you have the electric field force is approximately the absolute value of the change in the potential or the potential difference over change in the distance of the charge. Consider the map of equipotentials drawn below. Note that the diagram below shows equipotentials but not lines of force. Sketch the lines of force on the diagram below. Well, you want to start from your points of high electric potential and go to your point of low electric potential. So from here, you would draw the line and follow the path from highest to low. And then from out here as well. And like this. At what point or points is there a point-like charge? Is the charge positive or negative? Well, as a result, from sketching the lines of force in part A, we can see that all of the force lines are converging at a point around D. And because they are all converging towards D, this means that point D is a point charge, or is a negative point charge. It's a negative point-like charge because all of the field lines are converging at a point, and they're going from the highest electric potential to the lowest electric potential. Rank the electric field strength at points A, B, and C. It can be interpreted as the number of field lines in a set area. So, for example, if we look at the area around C, there could be a field line. But if we look at A, the field lines become more and more condensed as they approach the point charge. There's more field lines, with the greatest being around B because of its proximity to the point-like charge. Therefore, the highest would be B, followed by A, and then C. Estimate the magnitude of the electric field at the star in the diagram. Use 0.8 centimeters for delta R. Well, we know that an equation that we can use is E is approximately the absolute value of the electric, or the potential difference, divided by change in, or the distance between two equipotential surfaces. We will use 0.8 centimeters for our difference of R, and the two surfaces between the star are 5 volts and 7 volts. So we have 7.0 minus 5.0 to get 2.0 volts. And then we have 2.0 volts divided by 0.8. That's 10 to the negative 2. Because it is centimeters, so we could easily convert this to 8 times 10 to the negative 3. And then we can convert this to, and the 8, because it can be divided by 2, get 1 and 4. So then we have 1 divided by 0.004, which ends up being about 200 or 250 newtons per coulomb. If a negative test charge were to be placed at the star, which way would it be pushed? Well, we know that field lines are the path that a positive test charge would take, going from a high electric potential to a low electric potential. So if the test charge was negative, it would instead go the opposite way, from a low electric potential to higher. Therefore, it would go out and away from this point charge, or this point-like charge. Thank you for watching.